Good afternoon, good morning, good evening, good night. I don't know when you're watching, but thanks for watching. Today we're going to be covering section 11.7, single replacement reactions. And of course, I got my fifth period class here who's going to be helping me today with the presentation. Thank you, fifth period. All right, so let's get started. And of course, all of this information is from your CK12 packet. Why is the silver dark, right? If you've ever owned pure silver or you bought a James Avery necklace like I did a couple years ago, and it was actually about 5 or 6 years ago. I looked at it the other day because I was going to put it on, and it was tarnished. It was all black. So what am I going to have to do? I'm going to have to clean it, okay? And I'm going to tell you how to clean things that are tarnished with some household items that you probably have in your house. All right. Why is the silver dark? Yeah, Alexia, she's helping out her little sister. So I need somebody to help me with the introduction. Irvin. 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 Okay, Caitlin.
I'll read it.
Thanks, Oscar.
Why is the silver dark? The cup shown above provides an example of tarnish. A chemical reaction caused when silver metal reacts with hydrogen sulfide gas produced by some industrial industrial process or as a result of decaying animal or plant materials.
No, don't worry about the reaction. I'll read it.
The tarnish can be removed using a number of polishes, but the process also removes a small amount of silver along with the tarnish.
And here is your first example of a single replacement reaction. And the fact that it says single, that's probably going to tell you that a single element is being replaced, right? You can probably figure that out on your own just by looking at it. What is being replaced in this case? Who's doing the replacing? I got silver, right? Ag. Silver is replacing who in this compound? Hydrogen sulfide. Who is silver replacing? Who is silver replacing?
Hydrogen.
Very good. Thanks, Jeremiah. Yes, silver is replacing hydrogen. And you can see that you have hydrogen all by himself on the right, on the product side, and now silver has attached to sulfur. Okay, this is the reaction when silver tarnishes. Silver, right? The cup before all of this tarnish was pure silver, right? It was pure silver, it was nice and shiny, and it was pretty. But over time, it starts to react with hydrogen sulfide gas. And that could be because maybe you have some fruit that started to, decay or rot. Maybe, I don't know, it may be floating in the air because maybe there was a dead animal down the street. I don't know. But either way, you have some hydrogen sulfide gas somewhere and it's reacting with the metal. In this case, silver sulfide. So silver will react with hydrogen sulfide and produce silver sulfide. So you'll all of a sudden see these dark little marks all over your silver. And that's how it started. When I looked at my necklace, a couple years ago, I saw a little bit of dark spots. And I was like, it's fine. I don't really need to polish it. But I looked at it because I hadn't worn it in a while. It was in my jewelry box. All of a sudden, I take it out and I'm like, oh my God, what happened to it? It's all tarnished. Okay. And actually, Mr. Chavez, one of the teachers that helps me out, he said that you can use soda, Coca-Cola. If you use Coca-Cola, you can remove some of that tarnish that's on your silverware or on your necklaces or whatever you have that's silver. But every time you rub off that tarnish, you're going to be removing a little bit of the silver too. So that's how come, I don't know if you've ever walked around the mall, but I know I have when I was passing I don't know, like K Jewelers or, something like that. They saw me walking around, right? And they're like, oh, would you like your ring polished? And I was like, oh, sure, no problem. And and at the time I didn't really think about it, right? So I was like, hey, yeah, I could use a good cleaning, so it can sparkle, right? But when I started to look at the reaction and I started talking to some people who used to work at a jewelry store, they said that the rags that they use, they can take them and they can put them under a certain reaction, and they can remove some of the metal that they have taken, and they can add it up eventually and they can make something out of it. So yes, they're doing you a favor, but they're also taking a little bit, even though it's a very small amount. But if you're doing it over and over and over again for the full year, at the end of the year, you can probably get some gold back. So that's just a little FYI. Single replacement reactions. Single replacement reactions are very easy to identify, mostly because it's the only type of reaction where you'll have a single element on the left and a single element on the right. And they're not going to be the same element, right? They're going to be different elements, but they're very easy to spot because combustion reactions, it's always a compound, an element, and then compounds, right? So now we're looking, okay, it's an element, a compound, and then an element. So you're going to see that element, that single capital letter on both sides of the arrow sign. Very easy to spot one of these types of reactions. And the definition, I don't remember if I read it, but I'm going to read it again. It is a reaction in which one element replaces a similar element. And you see how it says similar? That's important also. Similar means metals replace metals. Non-metals can replace a non-metal, but you cannot have metals replacing non-metals. Okay? And it talks about it here. The general form of a single replacement, also known as a single displacement reaction, is here. And you have element A. Remember, element A can be any metal, and it can replace element B, another metal, right? And you can see that B is now by himself and A has attached to that C. In this general reaction, element A is a metal and replaces element B, also a metal. In the compound, when the element that is doing the replacing is a non-metal, it must replace another non-metal. And you have this general equation where now you have a non-metal Y replacing non-metal Z, and then you have Z by himself over here, and now Y has attached to the metal. And it says it again down here. Y is a non-metal and replaces the non-metal Z in the compound with X. All right, so look for those elements. Look for those single elements on both sides of the reaction, on both sides of the yield sign, the arrow. Okay, in case you forgot what the yield sign is, it's basically the arrow. All right, so here's your first Pear Deck question. I want you guys to go in there and I want you to identify these 5 reactions. All right, and first, before you do that, right? Before you do that, because we've already talked about 4 reactions. We talked about decomposition, combination, combustion, and now we're talking about single replacement. I can tell you that combustion is not in there. It's only combination, decomposition, and single replacement. I did not include a combustion reaction. I could not find one. Okay, so that's out. You're only looking for 3 types of reactions. All right. So go into Pear Deck and tell me how many or what type of reaction do we have from 1 through 5. And if you don't have the link, I just added the Pear Deck link again. All right. KKK. Kevin is here. If only Kevin would turn in his work. All right. Which one of these reactions is a single replacement reaction? And I'm waiting for a response from somebody so that we can use their page to discuss. So who's going to help me out? Who is going to help me out? Hello, anybody out there? Caitlin, Ms. Diamond, Oscar, Jeremiah, Irvin. Who's going to help me out with this Pear Deck question? Right here. I need somebody to tell me which one of these 5 do you think is a single replacement reaction? Where do I have a single element on both sides of my arrow? No responses on Pear Deck. How sad. Come on, guys. I need one person working on Pear Deck. Oscar says number 1. Let's check it out, Oscar. Okay, I agree that there are single elements on the left side of the arrow, but I don't see single elements on the right side. So that cannot be a single replacement reaction. Try again. Where do I have a single element on both sides of my arrow? Reaction number 2. Okay, let's check it out. Let's check it out. Reaction number 2 has zinc on the left, hydrogen on the right, and we can see why zinc replaced hydrogen, right? Hydrogen got booted, and now hydrogen is alone, and zinc is now attached to sulfate. Very good. Yes, that is a single replacement reaction. Can somebody hear? I don't know who this is, but can you write here that it's a single replacement reaction? I don't know who this is, but I'm asking you to help me out here. Thank you. All right. Which one else is a single replacement reaction? Which one looks like number 2? Which one looks like number 2, guys? What do you think, Ms. Diamond? Jeremiah? Which one looks like number 2? A single replacement reaction. Number 5. Very good. Number 5. Not number 4. I'm going to check out. Let's check out number 4 because this person already started trying to do number 4 as a single replacement. I'm telling you that it is not a single replacement because, don't delete everything. It is not a single replacement because I don't have single elements on both sides of the arrow. Number 5, Ms. Diamond. Yes, definitely a single replacement reaction. Oxygen was by himself, and look, he kicks out chlorine. Chlorine is alone, right? You can see that here. Oxygen is here. He kicks out chlorine. Chlorine ends up alone, and now oxygen has attached to selenium. So yes, this is a single replacement reaction. Very good. Much better. Very good. Thank you. What about number 1, 3, and 4? Which one else? Thanks, Irvin. Okay. So that's it for single replacement. Now we're looking for the 2 remaining reactions, decomposition and combination reaction. Which one is a combination reaction where you have small compounds coming together and forming one product or one compound? You can also have elements coming together and forming one product. Where do we have combinations? And remember, decomposition means to break apart. Where do we have a combination reaction? Number 3. Very good. Number 3 is definitely a combination reaction, right? You can see here phosphorus. Phosphorus was alone. Oxygen was alone. They combine to form diphosphorus trioxide. Very, very good. Yes, this is definitely a combination reaction. Which one else is a combination reaction? We have number 1 and number 4 left. Number 3, combination reaction, Irvin. Which one else looks like number 3? Number 1, very good, Miss Diamond. Number 1, we have copper combining with sulfur to make copper 1 sulfide. Combination reaction. All right, so what is the last type of reaction that you see here? You got a big compound breaking apart into small compounds. What type of reaction is that? You got a large compound breaking up into small compounds. What type of reaction is that? What happened, Irvin? Irvin got kicked out or what? I don't see you putting the names in here. We said number 3 and number 1 are combination. But what is this? What type of reaction? What type of reaction breaks things into parts or to small compounds? Very good, Miss Diamond. That is known as a decomposition reaction. Decomposition, the name says decomposition. That means that things are breaking apart. In this case, calcium carbonate is breaking apart into smaller compounds, carbon dioxide and calcium oxide. Very good. Thanks, Irvin. Thank you, Miss Diamond. Oscar, I appreciate the help. All right, so let's talk about metal replacement and hydrogen replacement. Magnesium is a more reactive metal than copper. When a strip of magnesium metal is placed in an aqueous solution of copper 2 nitrate, it replaces the copper. The products of the reaction are aqueous magnesium nitrate and solid copper metal. Okay? All right, so here we have the reaction. We have single element magnesium, which is very reactive, and they're telling you that it's more reactive than copper. So magnesium will bump out copper. Copper ends up alone, right? You can see the copper alone over here. Magnesium bumps copper. Copper ends up over here. And look, magnesium is now attached to nitrate. Everybody see that? This is a subcategory of single replacement reaction. So this is a type of single replacement reaction, but it's known as a metal replacement reaction mostly because metals are replacing other metals. In this case, metal magnesium is replacing another metal, copper. Boom, boom, he's by himself, right? And then you have hydrogen replacement. Many metals react easily with acids, and when they do so, one of the products of the reaction is hydrogen gas. Okay, so I know hydrogen is a nonmetal, miss. How can I have a metal replacing hydrogen? Well, there's certain exceptions to the rule, and this is one of them. Zinc will react with hydrochloric acid to produce aqueous zinc chloride and hydrogen. So here's your reaction. Zinc, a metal, is going to come in here and it's going to bump the hydrogen off. Hydrogen will end up alone and zinc ends up with chlorine. Okay? This can happen, but only for the nonmetal hydrogen. Okay? Only for hydrogen. In a hydrogen replacement reaction, the hydrogen in the acid is replaced by an active metal. And here is what it's going to look like. You can see the magnesium is like a silver color, right? And you can see it here. The liquid in this test tube is hydrochloric acid, a very dangerous acid. And you can see some bubbles forming. Those bubbles are hydrogen gas being released. So zinc will bump off hydrogen attached to chlorine, right? Hydrogen will go off. It'll get released in the form of gas, and you'll be left with zinc chloride. Zinc chloride. Let's continue. Some metals are so reactive that they are capable of replacing the hydrogen in water. So again, we're talking about metals replacing hydrogen in water. The products of such reactions are metal hydroxides and hydrogen gas. All group 1 metals undergo this type of reaction. And remember, your metals for group 1 are right here. Lithium, sodium, potassium, rubidium, cesium, and francium. All of these guys can replace hydrogen in water. And only one hydrogen, not both. Check this out. Sodium reacts with water. Remember, think of water as H, O, and another H over here. So it's going to bump off one of the H's and hydrogen gas is produced. The other H will stay and create a hydroxide. So you'll have sodium hydroxide. All right. And it says here, sodium metal reacts vigorously with water, giving off hydrogen gas. Sometimes if you have a large piece of sodium, it will often make enough heat that hydrogen gas will ignite. And you'll see kind of like a little fire kind of blast. The element chlorine, halogen replacement. Remember, halogens are over here, group 17, halogens, right? So let's talk about halogens. The element chlorine reacts with an aqueous solution of sodium bromide to produce aqueous sodium chloride and elemental bromine. So here's one halogen, chlorine, and it's going to replace bromine, another halogen. It's going to bump up bromine. Bromine will make a gas in the liquid form. A diatomic molecule in the liquid form, and you end up with salt. Aqueous means in water. You'll have salt in water and bromine in the liquid form. The reactivity of the halogen group. How reactive is this group? So you'll have the very reactive elements at the top of the group, and it's going to reduce as you go down. Fluorine is considered to be the most reactive halogen, while iodine is the least reactive. Since chlorine is above bromine, it's more reactive than bromine and can replace it in a halogen replacement reaction. So let's go to the periodic table. What are they trying to tell us? They're trying to tell us from this group, fluorine can replace anybody below him. Anybody below him, fluorine can replace. Chlorine can replace anybody below him, but he cannot replace fluorine. Bromine, again, can replace anybody below, but he cannot replace chlorine and he cannot replace fluorine. And then the same thing for iodine. Iodine can replace astatine, but he cannot replace fluorine, chlorine, or bromine. Above cannot, the ones on bottom cannot substitute for the ones on top. Only the ones on top can substitute for the ones on bottom. Why? Because these guys are more reactive. Fluorine is the most reactive of all the halogens. Excuse me. And that's what it says here. Since chlorine is more reactive, it's going to bump out that bromine. All right. I need one person on Pear Deck to transcribe the word problem below into a skeleton equation, and then I need somebody to balance. Who's going to try that one? Who's going to try and write the reaction where lead reacts with phosphoric acid to produce hydrogen gas and lead 2-phosphate? Who's going to write that out for me? And the formulas are here. This is your first element. This is the compound. This is an arrow, right? Arrow means to produce. So you're going to put hydrogen. and then lead 2-phosphate. I need somebody to write that reaction for me. There we go. Good job. Is that you, Irvin, again? Very good. So he's putting lead. He's putting phosphoric acid, hydrogen gas, plus lead 2-phosphate. And I'm pretty sure that's what he's going to do right now. It's a 3, not a 2. Be careful. Oh my God, I need to stand up. I'm tired of sitting down. 2 hours of just sitting down is annoying. Oh, very good. Okay, take off the parentheses at the very end after the 2. Leave the 1 in between the 4 and the 2. No, yeah, that one. Leave the other one. Okay, great job. Okay, that's our reaction. Irvin, I'm thinking it's Irvin. Irvin wrote the reaction for us, right? He says that PB, oops, might help if I have a marker. PB plus phosphoric acid, H3PO4, yields or produces hydrogen gas plus lead phosphate. Very good, Irvin. But that's a skeleton equation. So we already did that. That's out. We need to balance appropriately. Okay? So what's my list? Who is part of this list of elements that I'm dealing with in this reaction? And somebody can come off mute and just tell me. You don't have to write it. Ah, very good. So he started with PB, hydrogen, and I want you to put PO4 together. And the reason why, Irvin, is because PO4 shows up on both sides of the arrow. If you see a polyatomic, which this is a polyatomic, if it shows up on both sides of the equation or of the arrow, then you keep it together. It's going to make your balancing life a lot easier. Very good. So PB is 1. Hydrogen, oh, very good. 3. Hydrogen, 3. Hydrogen over here, 2. Now, this one's a little bit tricky, Irvin. Hold on. Let me show you. This guy has an imaginary parentheses and a number on the outside. What is the number outside of the parentheses that you cannot see? A 1. Very good. Continue. Very good. Where are you going to start balancing? You have a 3 and you have a 1. What's going to happen? Very good. So that's going to equal 1. 3 times 1, guys. How many? 3. Very good. So let's put that 3 in front of PB. All right, we want to put the 3 in front of PB. All right, very good. Okay, what about the 3 and the 2? I'm going to multiply 3 by the opposite number. What am I multiplying 3 by? What's the opposite number on the other side of the equation? So I'm going to put times. And what's the number? 2. What's 2 times 3, guys? Over here, what's the opposite number? 3. Very good. Very good. So where does this 2 go? The 2 goes in front of hydrogen, right? So let's put that 2 in there, Irvin. Okay, where's hydrogen over here? Where am I going to put the 3? Where's hydrogen? Where's hydrogen? Where does that 3 go? Very good, sir. But let me ask you a question. When you put the 2 here and you put the 3, that's good. Who else got affected? Who else also got multiplied by 2? PO4. Very good. So let's go over here on bottom and let's multiply or just take it off and 2. Very good. Very good. So look at your numbers, guys. You got a 3 and you got a 3. You got a 6, you got a 6. You got a 2, you got a 2. Great job, Mr. Irvin. I think you got this balancing thing pretty good. I think you're doing really, really well. I hope the rest of you guys are understanding it. Oh, it's Miss Diamond, not Irvin. Thank you, Miss Diamond. Appreciate it. All right, Miss Diamond definitely knows how to balance. Great job, bam. All right, let's watch a video and then we're gonna close it up.
If you're asked to predict the products from a single displacement reaction, how do you do it? Step 1, figure out whether or not the element that you're given will replace the metal in the actual compound. Here we're asking, will magnesium replace copper? To figure that out, you need something called the activity series. This is probably a chart that your teacher gave you, or it's in your textbook. What it is a list of a whole bunch of different metals, from most reactive to least reactive. The higher an element is in this list, the more it will replace other elements. Put another way, magnesium will replace copper if it's higher in the list. Well, see magnesium here and copper way down here. Magnesium is more reactive, and so it will replace copper. So we will have a reaction. If magnesium had been lower, we would have just said no reaction. That would have been our answer. We'd be done. But it does replace it, so we gotta keep going. New question is, what ions are now paired? Well, let's see. Magnesium is going to replace the copper. The copper is going to get booted out. So, first of all, you're going to end up with copper left over. Then, how does magnesium bond to fluorine? This is where you need to know your ions. Magnesium is in the second column of the periodic table. See, it's right there. You guys can't see it. It's right here. Magnesium loves to form the ion 2+ because it wants to lose 2 electrons. Fluorine wants to gain 1 electron. It usually has a charge of -1. And to actually figure out what the compound is, you have to crisscross those charges, at least that's what my teachers like to call it, and you're left with Mg1F2. Notice I didn't write the little subscript 1 because that's just convention. So, if you put solid magnesium in a solution of copper fluoride, the magnesium would replace the copper and you'd end up with solid copper and magnesium fluoride. It's kind of a cool reaction. Now, you could be asked to do this for several other reactions. Let's see what we can do as quick as we can. Silver plus sodium chloride. Will silver replace sodium? According to my chart, silver's down here, sodium's up here. Silver is lower, so silver will not replace sodium. We're done, no reaction. Will calcium replace tin? Let's take a look. Calcium is way up here, tin is way down here. Yes, it will, because it's higher in the list. When calcium boots the tin out, you're going to end up with tin by itself, and calcium, which is usually 2 plus, bonding with nitrate, which is usually 1 minus. Crisscross your charges, you end up with Ca1 and O3, 2. Done. Will aluminum replace copper? Aluminum is up here, copper's down here. Yes, it will. Aluminum boots out the copper. The copper is all by itself now, and aluminum is bonded with sulfate. Aluminum is 3 plus, sulfate is 2 minus. Crisscross. Al2, SO4, 3. Done. Will sodium replace hydrogen? Now, sodium is way up here, hydrogen is way down here, so yes, it will. Now, I've included this one because it's an exception. It's a little bit tricky. Sodium will replace hydrogen, but
Pay attention to this one, this last one, because it is going to be part of the questions that you're going to do for number 4. One of the questions from your review questions, okay? So just watch this carefully.
doesn't replace both hydrogens in water. Just watch it. This only really happens for water. You need to consider water to be like hydrogen hydroxide. HOH. See, there's still 2 H's, there's 1 O. This is just another way of writing it. The sodium really only boots out 1 of the H's. So, you'll end up with hydrogen by itself. Hydrogen by itself is H2. It's one of those atoms that makes, what are they called? Diatomic molecules. There's 2 atoms in each of the molecules. And sodium is now bonded to hydroxide. Now, sodium is +1, hydroxide is -1. Crisscross, and you get NaOH.
Okay. So that is a reaction that you're going to have to consider today in our presentation. All right. So in summary, the activity series describes the relative reactivities of metals and halogens. Review questions. What is a metal replacement reaction? Will a non-metal replace a metal? What is the most reactive halogen? And what products will I get if I add potassium metal to water? All right.